Okay, just confirm if my screen is visible once.
No,
No,
sir,
sir,
right
right
now
now
it
it
is
is
not.
not.
It is not over. Just wait. Hope my screen is visible now.
Yes, sir.
Yes, sir.
Okay, and in between also ask a question. Okay, so that I feel that you people are understanding. Okay, so let me start. It's from your unit 2, I think, if you have seen your syllabus, correlation and covariance.
Yes, sir.
Yes, sir.
Okay, so correlation and covariance, somehow it's related, and you people might have heard of this term earlier, because in data science, maybe in your every single subjects which are related with the data science, or maybe your marketing, maybe some other subjects, even in finance, you might have heard of this correlation at least. Okay, so coming to this correlation and covariance, we will try to cover obviously the causation part as well. Causation is not in your syllabus, but at least you should understand what is causation, because correlation and causation. Okay, sometimes people understand whenever you find correlation between, let's say, two variable, you jump on to say that it's due to some causation. Okay, I'll let you know how correlation and causation is different. Okay, and covariance is nothing but, you can say, it's a kind of some of the interpretation of correlation only. Okay, but majority of the time in data science project, when you work on a data science project, you just work on this correlation part, because the correlation help help you out in feature selection as well. If you people might have worked on any data science project related with any, you can say, maybe the regression, or for example for any ML algorithm training, at that time the coefficients of this correlation help you out to figure out which, you can say, the variable is to select. Okay, so correlation is very much important, the weight of the correlation. Okay, similarly, there is some matrix. I'll let you know how you can you know create correlation matrix. And then coefficient of correlation, it's more important, coefficient of correlation, because it will give you some direction that in which direction two variables are moving. And I'll show you through Python programming how you can create correlation matrix and how you can check correlation between two variables. Okay, because correlation means, obviously, co means two, between two. You cannot find correlation between three variables. You have to pick two at a time and neglect others. Okay, so coming to this correlation, so this visual, if you see, there are two, you can say, this line. One is MACD store, let's say 31,046 number of MACD outlet were there in 2006. Okay, now it has, in 2018, has gone up to 38,695. Okay, and same goes with your inflation. If you see the inflation part, if you see the inflation part, the inflation has started, let's say, inflation about 202, maybe it's in rupees, let's say, and $256 was the inflation, let's say, in 2018. Let's say June, it's 2018. Okay, so when you plot the graph between the number of MACD outlets, okay, MACD outlets and the inflation, okay, so you will see there is some kind of a correlation. Okay, there is some kind of a correlation. So it doesn't mean that the number of, as you are increasing the number of MACD outlets, it's causing inflation. So you can't say in that way that the reason for inflation is the number of MACD outlets. Okay, if you are increasing the number of MACD outlets, your inflation is also increasing. It can't be said in that proportion that it's a causation, but there is strong correlation between the number of MACD stores and the inflation. You can say the consumer price index. Okay, they are highly correlated, but it's not that it is causing the number of restaurants are causing inflation. You cannot conclude that. Okay, similarly, so did Twitter users increase Tesla's share price? If number of, let's say, Twitter user is increasing, the Tesla price is also, let's say, increasing. They are highly correlated. Okay, as the number of, let's say, people are tweeting more about the Teslas, maybe their share price is also increasing in some, you can say, in some quantifiable terms. Okay, but two things are highly correlated: the number of, let's say, Twitter users and the share price of Tesla. They are increasing in some proportion. So these two variables, you can say, are highly correlated. But can you say, is it the single reason why Tesla price is increasing? You can't. Okay, so correlation means there is some relation between the two variables, but whether one variable is causing others to happen or not, that can't be figured out from the correlation. Correlation will only tell you the direction in which two variables are moving, how strongly two variables are associated, that's all. But in causation, you require intervention of third variable to judge whether the reason for Tesla price is the number of Twitter's users is not is the reason, single reason or not. For that you require some kind of a external variable. For that there comes a concept of experimental design. You design some experiment to check the causality. Okay, so one more you can say the visuals. Is the price of Bitcoin a leading indicator for avocado sales? Okay, as the number of okay, I thought someone wants to join. As the number of, you can say, the price of Bitcoin is also increasing, you can say whether the avocado prices, their sales is increasing or not. Okay, so if you plot it out, the Bitcoin price, you will see there are some peaks here. Okay, if you see this one, there are some peaks and there is some valley. So as Bitcoin price is increasing, you see the avocado price has fallen down. Okay, but here you can see the avocado price has increased, but Bitcoin price has decreased. So in some cases you will see there is some increase in Bitcoin, or maybe increase in the avocado price, or maybe increase in the Bitcoin, there is some downfall in the avocado price. Okay, but these are the cases which are highly correlated, but it is not the reason. Causation means the one variable causing other to happen. Okay, but here it's not the case. So these three variables I have shown you in a way that the two variables which are highly correlated, but they are not the causal, you can say the cause and effect. Okay, so now it's time to define the correlation. Okay, so if you see this one, the degree to which two variables move in coordination with one another. Okay, so here let's say you have a two variables, maybe the sales and revenue. We have a two variables, whether they move in accordance with one another or not. Let's say you are increasing the sales, so revenue is increasing or not. If you see sometime, if your sales increases, obviously your revenue increases, obviously. Okay. So but sometime if you are putting high discount, okay, and also you're just subtracting the operating cost and all, in that case you will see even sales are increasing but revenue is not increasing in that way. Okay. So one variable increase in one variable may possible decrease in other variable. Okay. So the correlation means the degree to which two variables move in accordance with one another, in coordination with one another. They coordinate. Okay. So there are a possibility of two variables moving in the same direction. Let's say if you are increasing sales, revenue will increase. Sometime, for example, I have given you one example, GDP versus inflation. Maybe some case if you increase the GDP, inflation decreases. In some cases, if you increase the GDP, maybe inflation also increases. Okay. So when they move in opposite direction, you say the two variables are negatively correlated. They have a correlation. Obviously, they are moving in coordination with one another, but in negative direction. Okay. For example, if you see the height and weight of, let's say, kids, okay, so the height is 60 inches, the weight is, let's say, 120 lbs. Okay. So if you see this chart, you will see as per the height, weight is also increasing. Okay. So weight and height is highly correlated here. Okay. So they form some kind of, you can say, association between the two variables. Okay. But whether height is causing weight or not, that you can't conclude here. But by looking at this height and weight, you can say yes, those who have a height have a higher weight. But here, if you see the 64, the weight is 150. Okay. But if you see the 63, the weight is 160. Okay. So there are some, you can say, the data points where we have not in accordance with the weight and height. Okay. But if you plot it out, you will see some kind of a correlation, maybe the high correlation between the height and weight. Okay. So that is one of the you can say the good example of the correlations. Okay. Because there are two variables you can easily check, and at least the correlation part, that will give you an idea whether two variables are highly correlated or not. Okay. So coming to this correlation analysis, there are some, you can say, different correlations, positive, negative, and there are something called zero correlation. Okay. So as I already told you, height and weight. Okay. So if you plot it out, the graph between height and weight, you will see some kind of a positive correlation. Okay. They are highly correlated. Okay. So positive correlation means if one value of attribute A, let's say the variable A, increases with the value and increases with increase in the value of, let's say, attribute B, and the vice versa. Let's say if B increases, A increases, and if A increases, B increases. In that case, you will see there is a positive correlation. The two variables are moving in a positive direction. Okay. Similarly, there is something called negative correlation. Okay. If you are increasing variable A, the B will decrease. Let's say if you are increasing GDP, inflation is decreasing. Okay. Similarly, zero correlation means there is a no, you can say, relation between the two variables. Okay. If you are increasing one variable, maybe second variables are varying but in a very random fashion. Okay, so you don't have any clue that how if two variables are anyway connected or not. Okay, so they are randomly, if two variables are randomly associated, then you can say there is a zero correlation. Okay, so coming to this correlation graph, if you see, positive correlation means, let's say if you are increasing sales, revenue will also increase. So this is called a lineup based fit. Okay, because when you are plotting this, the points are, you can say, equally distributed, the points. Okay, so this is lineup based fit and error can be minimized. So I'll teach you in this linear regression class how you can leverage correlation to plot a regression line that is a lineup based fit. And this is positive correlation, means if you are increasing one variable, other are are also increasing in coordination with one another. Okay, so now coming to this zero correlation. Zero means even if you are increasing, they are randomly, you can say, increasing or decreasing. They don't show any kind of correlations. So this is a zero correlation, kind of a static, you can say, zero. When you plot it out, you will, the correlation coefficient, it will give you a kind of a zero value, approximately a zero value. Okay, so then coming to this negative correlation means if you are increasing, let's say, GDP, the inflation is also decreasing. So this will give you a negative correlation. Okay, so in many cases, for example in business case, you have to check whether your two variables, how they are behaving, whether they are increasing or decreasing. So majority of the time you will deal with this positive and negative correlation. The variables which doesn't have any no correlation, that is good. But when we have a positive and negative correlation, high correlation, in that case you try to pick one. Okay, that is why in a regression case you try to create a correlation matrix to check how two variables are correlated. Okay, for feature selections. Okay, so correlation analysis, if you see this one, then if students are let's say putting, let's say, 6 hours and their marks are, let's say, in this case if someone is putting 6 hours, their marks is 70. Okay, so it's a kind of a positive correlation. Okay, if someone is devoting 1 hour, their marks is, let's say, approximately 40. Okay, so you can see that hours of study and the marks are highly correlated. But can you say that it's the only the number of hours you study? You can't say that, because there is some third factors. For example, some students are so smart that if they study for, let's say, 1 or 2 hours, they can easily grab the concept. Okay, so the idea behind causation is that the intervention of third variable, which we can't see using this correlation. So correlation only can't tell you the story of causation. And every time if you see this correlation doesn't jump and say that the reason for causation is also the number of hours, let's say in this example. Okay, so never jump and say correlation is causation. Okay, because there is some intervention of third variable which we can't see. Okay, and if you have that variable, then only you can conclude correlation and causation. Okay, so coming to this correlation coefficients, as I already said, the coefficients is more important. Okay, the coefficients, if you see this coefficient, if two variables has a coefficient of, let's say, more than 0.5, then you can say your two variable has a strong correlation. If it has highly negative correlated value, then you can say it's highly correlated but in negative way. That is a negative correlation, but high negative correlation, more than minus 0.5. Okay, so these two coefficients will help you out in future selections. Okay, because when you train a machine learning models, let's say if you have a 15 such variables, so you cannot use all the 15 variables. Okay, so if you have to remove some variables, because machine learning algorithms can't be trained on you can say the more than, if you have more variables, then you are training your ML models, it's not a good idea. At least you have to remove some variables to come up with a better you can say a model. Okay, if you see this one, so just remember that strong if has a value more than 0.5, and negative correlation highly if have a value more than minus 0.5. Okay, otherwise the two variables are weakly correlated. Okay, now so plus 1, if the R value, R means correlation coefficient value, plus 1 imply that perfect positive correlation. So the correlation value, the coefficient of correlation will always lie between plus 1 to minus 1. So plus 1 means two variables are highly correlated, let's say sales and revenue. And let's say minus 1 means GDP and inflation, let's say. They are correlated but negatively correlated. If you are increasing one variable, other variables are decreasing in coordination. Okay, and R equal to 0, it means there is a no correlation, means there is a no relationship between the two variables at least. Okay, so these are the you can say these are the way in which you can interpret coefficient of correlation. Okay, now let's say I have given you this chart, okay, this data point. The advertisement expense, let's say these are in dollars, million dollars, let's say 9 million you have spent in advertisement, and the sales which you had was 19 million, let's say. For $9 million of advertisement, you are capturing $9 million of sales, annual sales. Okay, and same goes on to let's say 4 million of advertisement, and now you have a sales of around $8 million annual sales. So by looking at this data points, you can easily see one is let's say increasing, other is also increasing. Okay, somehow there are some points where it is decreasing. Okay, but if you have a larger data points, it will be difficult to understand whether two variables are had some correlation or not. Okay, so when you go through some softwares, maybe in Excel or Python, there are many softwares available with you, some programming languages. So if you calculate the correlation coefficients let's say between marketing cost and serial sales, and when you check the correlation coefficients, how marketing costs and sales are related, you see they are showing 98% of correlation. Means if your marketing cost is increasing, the sales is also increasing. So this will give you a clue, as let's say if you are a business analyst, or maybe you are designing some marketing campaign, by looking at this chart you can also design a marketing campaign. Okay, that when you are increasing the marketing cost, your sales are increasing. So there are different way of marketing, whether you want to go with the billboards, maybe the physical marketing strategy, or you want to go with the digital strategy where you can leverage different social media platform. So this correlation will also give you a clue. Okay, you can at least decide, you can come up with certain decisions. Okay, and also you can formulate some strategy. So that is why this correlation is a, you can say, the starting point, how you can decide. Okay, so let me show you this correlation. One how correlation. So using Python, Jupyter notebook. Okay. So in correlation, yeah, this one. Just see how you can use this correlation concept. Just see. Sorry. So import numpy as np, as I already told you this one. These are some libraries, pandas and numpy. Okay, and you are reading the file CSV file, which is stored here in CSV format, and we are seeing dataset.head. So dataset.head will print us a 5 records, the first 5 records. Just remember. Okay, so just run it, this one. So when you run it, it will print you first 5 records. And what are the, you can say, the variables, but these are the features, you can say. The TV, radio, newspaper and sales. There are the 4 columns here. But unnamed, let's say, this is just a numbering. So here we can remove it, but let it be here. Okay. TV, radio, newspaper and sales. Okay. So now it's a small command, just dataset.cov means covariance. Okay, it will show you a covariance. If I run it, it will give us covariance, means how TV and TV, let's say how they are covariated. Okay, but this will give you minus infinity to plus infinity value, the covariance matrix. But it's just you can say the reverse of correlation, you can say. Somehow it is giving you a value which are you can say continuous values. So it's very difficult to interpret sometimes. How you are going to interpret it? Very difficult, the covariance matrix. Okay, so now when you run this correlation matrix, dataset.corr is a function, and we are passing a method called Pearson correlation. There are different methods of correlation, but majority of the times you will use this Pearson correlation. You are passing the argument, we are saying you just give me the correlation matrix, but it should follow this Pearson correlation matrix. Okay, just run it. If you run it, you will see this Pearson correlation matrix. This is a matrix. Okay, now just see TV and TV. The value is 1, means these are highly correlated. Means if you are passing the TV and TV, obviously the correlation will be high because it is the same variable. Okay, so diagonal is 1. Just see, the diagonal is 1 because it's a correlation of the same variable. But if you see radio versus TV, the correlation is 0.05, which is kind of a low correlation. Okay, but see this one, 0.576, it's a radio versus sales. The correlation is higher because it's more than 0.5, so you can pick up this as a highly correlated variable. Okay, so now coming to this correlation matrix, this correlation matrix again, and I'll tell you what, this is a Seaborn library just to plot a visual graph. So just see this one, there is something called a heat map. Okay, so we are passing this correlation matrix. This is from above, you can say command correlation matrix, because our entire matrix is stored in correlation matrix. So we are passing correlation matrix here, and we are saying the X and Y labels, and we are saying the you can say the colors if they are highly correlated, and we are annotating, means annonation means you can say the names and alls, and with 0.5 you can change it, all these things, okay, as per your requirement. But if you run it, this will give you a plot like this, you can say the visuals like this, okay. So when you do this regression, the problem, ML problem, so this will give you a diagonal is 1, okay. Now you are able to interpret it easily, okay. So TV, and let's say one more, a TV and newspaper, TV versus newspaper, the value is 0.05, which is showing negative, you can say the low correlation, but here you can see 0.7, that is sales versus TV. So highly correlated value, just see this one 0. This is the same. Now the value which are negatively correlated, just see newspaper versus unnamed, which is not required here, but if you see this one a value which is less than 0.5, yeah, this one 0.23, sales versus newspaper. So you will have an idea which are highly correlated and which have a low correlation. This one 0.78 and 0.58, there are two variables which are highly correlated, and there are variables which have a lower correlation here, okay, and these are showing zero correlation here because 0.055. So this is how you can interpret how two variables are correlated and which variables you have to pick. Let's say this is showing 80% of correlation, okay. If you have a 10-12 variables, you will remove one, okay. Either you will keep TV or sales, it depending on the feature selection, which feature you want in ML algorithms, okay. You can't keep TV and sales at the same time. Either you keep sales or TV, but you cannot destroy, you can say, the essence of ML algorithms, because if you remove, let's say, TV, if this variable is important in let's say in decision making or not, okay, if it is not interfering in your decision making, then you can remove TV. But if it has an influence, then you have to keep it, okay. It depends on the data analyst, how they want to perceive, okay, and which features they want in their ML algorithms, because ultimately they want to decide some strategy or maybe some kind of decisions they want to take only based on those variables which they take into account, okay. So this is how you can run correlation and covariance, okay. So this you can say this visuals will help you interpret how two variables are correlated and which one you want to pick, okay. And this is also called heat map. So this is one way of data visualization, how you want to visualize the data, and this visuals can give you a lot of insights. So this is called a heat map because they are using different colors, okay. That is why it is called a heat map, but they are in the matrix form, okay. Now coming to this covariance, it's just kind of a maths covariance, okay. It's just a formula. If you have a two variable, let's say sales and revenue, then how you can calculate the covariance. So here only the important part of covariance is that it can take a value minus infinity to plus infinity, okay. And if some positive value is there, it means two variables have a positive you can say relationship. So covariance is not that much important, but correlation, because we typically use it in our analysis, okay. So the covariance, as I already showed you through Python, because they are just numbers here, okay. They are different numbers here. So the different numbers, these are some you can say in the continuous form. and it's very difficult to understand that which are highly correlated, because you have to see. Okay, because as the numbers are continuous, because let's say 7370, okay, very difficult to say whether they are highly correlated or not, because you have to see the every numbers. Okay, but when you plot the correlation matrix, because it's between -1 to +1, if the value is more than 0.5, you can easily figure it out by looking at the visuals, by looking at the heat map. That is why we typically prefer correlation matrix. Okay, now coming to this causation part. Causation means that one event causes another event to occur. Okay, causation means whether, let's say, if you have two variables, and the intervention of one variable is causing other. Okay, so let's say if there is some more humidity, and due to more humidity, rain, let's say rain started, you can say the rain has started. So maybe the reason for the rain to happen was your humidity, the level of humidity in the air, right? So that could be the one reason. Okay, it means one event causing other to occur. That is a causation. Means the cause and causal effect, cause and effect. Okay, the cause and effect. So causation can only be determined from, you can say, there is something called experimental design. As I already told you, in market research and marketing research, I think people do work on this experimental design. How one variable has effect on other. How one variable is causing other to happen. Okay, that is the case of experimental design. That you bring and you can say the external variable, that is called a stimulus. Okay, so there are different ways, so we can conclude that treatment causes an effect. So when you people might have if you see the experimental design, if you have read it somewhere, they bring some treatment group. Okay, and then they see whether they are causing or not, okay, that event to occur. So in ANOVA, if I will cover it, then I'll let you know how the analysis of variance is one of the, you can say, experimental design methods. They use experimental design concept to come up with this causation. Okay, so if you see correlation versus causation, just see due to the traffic jam. Okay, so let's say sometime you have a bad mood and you sometimes get tired. So when you enter inside your home, let's say your mom is saying, why you look so tired, and your mom says, yeah, it's due to the bad mood, right? So it's not the bad mood that is causing you tired. Maybe it's due to the long hours traffic jam. Okay, maybe in Delhi Gurgaon road. Okay, maybe somewhere in Noida. Okay, so this is missing, but people are saying it's due to bad mood, you are tired, but the reason for your tiredness is traffic jam. Due to traffic jam, you had a bad mood now and you are feeling tired. So this is the cause of tiredness, not the bad mood. So when you plot, let's say 100 people's bad mood versus tiredness, you will see it will show highly correlation. But we are missing this variable, traffic jam, the causation part. The traffic jam is causing bad mood, okay, and traffic jam is causing tiredness. But we are just capturing bad mood versus tiredness, and we are missing this traffic jam. Okay, the reason for tiredness and bad mood is a traffic jam. Okay, so that is why correlation and causation people do confuse. Okay, similarly, you see, if you see the lack of RAM is causing the text message, your phone are not able to send text messages, and your let's say phone is freezing. Okay. So when you plot it out, phone freezes versus text message won't work, you will see highly correlation. But the reason for these two is lack of RAM in your phone. Okay. Similarly, if you see in e-commerce company, the majority of the time in Amazon you will see people do some kind of cart abandonment, okay, and they uninstall it, okay, maybe due to the design, you can say the UI design. If there is some problem in UI design, so people do uninstall it, and when you go on to pay, you just stop, just you come out of the app, okay. So the reason for this lot, let's say if purchase is not happening, the reason could be the, you can say, the too many steps in purchasing. Let's say if you have designed an UI in a phone that has, let's say, 5-6 steps to reach out to, let's say, sales, when people want to purchase, so you have to reduce the number of steps, okay. So this will help you out also in designing UI, that is called, you can say, design experiment, okay. So as I already said, the correlation coefficients and all, okay. So now just see how you can calculate the correlation, okay. Let's say age and glucose level. The age is 43 and the glucose level is, let's say, 99, okay. Now you have this number of data points, okay, 5-6 data points. Now you want to find correlation. How you can calculate it mathematically, okay. I have shown you through Python. Now how you can calculate it through mathematically, okay. So the age and glucose level, let's say age is X and glucose level is Y, okay, because you need two variables, X and Y. Now we are just multiplying X and Y, okay. So there is formula of correlation, okay. I'll show you here. So now we are calculating X and Y, okay. We will multiply it, and then we have multiplied X and Y, glucose and Y, that is your age and glucose level. Then X square we have calculated, then Y square you will calculate. We have this you can say the calculated values. We have X square and Y square, okay. Now if you see this one, you have to put in this formula, R equal to, this is correlation coefficients. You just, if you have a, let's say, 5 data points, you have to sum it up, okay. And we have a calculation, let's say summation of X and summation of Y, and now we have calculated all these things. So when you put all these things in the formula, the glucose and age have a correlation coefficient of 52%, let's say, and we are saying 0.52. It means the age and glucose level are highly correlated. But the reason for glucose level is age is not that you can't say. That is a causation part. But at least you can say there is some correlation, okay. Similarly, in R programming, if anybody has a background of R, you can calculate using R programming. I'm just running it through the slides, okay. So we have a 3 data points, let's say 45, 38, 10, let's say it's just a data point, and you just want to calculate the correlation. This is correlation matrix. So in R, you can run it like this. Up to 2 digit, means 2 digit decimal, up to 2 decimal place, you just want the value. So the values are, let's say, 0.52 and 52. So A and B are highly correlated. If you see B and C are highly correlated but in negative way, okay, and you can see just their diagonals are 1. So this is how you can read how 2 variables are correlated. A versus A will have value 1 because these are the same variables. You are saying correlation of the same variable, so it is giving you 1, okay. So as I already showed you, this is your heat map, okay, and the value which are highly correlated are colored in black, and which have a slightly lower correlation or in a orange color. Okay, so you can easily see how two variables are correlated. Okay, so correlation matrix, as I already showed you, so just read it out this slide. Now, so there are some applications of these correlations. Okay, so you will find correlation in every single industry if you are, if you have some quantifiable data, if you are capturing data in numbers. Okay, in business, government, education, medicine, agriculture, everywhere, because we are have some numerical data, and we work on, majority of the times you work on numerical data somehow through different, you can say, the surveys and all, right? You capture the data from the you can say from the society, from the market. So if you see this the correlation in agriculture, so weather condition, productivity. Okay, now we have a chart of, let's say, weather conditions. Okay, so rainy season, let's say how much rain happened and whether it has hampered productivity or not. Let's say it has helped increase in productivity or not. If you have that chart, you can plot the correlation matrix. Okay, similarly, irrigating and productivity. Let's say if you have a high agriculture land which you want to irrigate. Okay, so if you have available, let's say, water, and now you want to capture the productivity, the fields which you haven't irrigated and their yield versus the field which you have irrigated. Okay, and there are different way you can capture the correlation if you have two variables and the numbers are in quantifiable terms. Okay, similarly, in medicine, if you see, let's say you want early stage of drug development. Let's say in COVID, during COVID time, people were struggling with the drug development, right? So at that time they used to test with different you can say the body, different age group, different medical conditions. They used to take used to check whether the drug are have some the effect on the body or not. Okay, so this can help you out also. You can check the correlations, and there are different, you can say, the way to check correlations and different applications here. Okay, so correlation doesn't mean causation. Okay, if you see this one, as I already told you since beginning, ice cream sales and sunglasses sold. Let's say if the sunglasses their sales are increasing, the ice cream sales are, let's say, also increasing. Whether they are whether this sunglass, the increase of sunglass is pushing ice cream sales higher, is this the cause? No, they are highly correlated. Okay, but it's not the sunglass, this is causing ice cream sales to increase, right? So you have to be very clear about correlation and causation. Okay, if you see this meme, the region, if you see the this van is moving and this guy is pushing. Okay, so if you see this one only, people will feel that they are highly correlated because they are moving in the same direction. But the reason for, let's say, car to move is these two guys, because they are pushing. Their effect is less. There is no effect. Still, he is just pushing. Okay. So maybe as the car is moving, if you check their correlations, maybe their effect, you will see some kind of a correlation, maybe higher correlation. But the region is here, these two guys. Okay, the causation is somehow which are invisible. So whenever you see the correlation, you just figure it out. There is some causations which are not visible. Okay, and you have to find it out. So what is the reason? What is the cause and effect? Okay, so in real life applications, let's say a researcher measured the shoe size and math ability of a large group of children. She found that having a large shoe size does not indicate that a child has more or less math ability. What does her analysis show? Okay, so maybe there is a higher correlation, maybe, but may or may not be the causation. So you require further study. That means you require intervention of a third variable. Okay. So that is called experimental design. Okay. So the B is right answer here. Similarly, if you see a grocery store collected sales data, it found that when customers buy less bread, they tend to purchase more rice. What we can conclude. Okay. So maybe you can say there is a correlation among the bread bought and the amount of rice purchased. There might be the higher correlation, but there may or may not be the correlation. Okay, so for that you require some kind of more, you can say, intervention kind of a study. Okay, to come up with the conclusion that the amount of bread we are purchasing is causing the rice to be purchased. To come to that conclusion you require some kind of a further studies. Okay, so that is why you never jump on, whenever you see any kind of a correlation, never jump on to say that it's the causation also. Okay, so coming to at the end, as I am focusing on this class since beginning, that correlation does not equal causation. Okay, because there are variables which are highly correlated. It looks so quantifiable in your data sheet. Maybe if you're using in softwares, it will let you push you that two variables are the reasons, maybe the one causing others. But always remember, correlation does not equal causation. Okay, so this is all from my side. If you have any question, you can ask. Okay, any questions so far?
No, sir.
No. 1 minute, let me take attendance. Okay.